I can't resist discussing what is probably the most famous supernova of the recent times. Many of you are too young to remember this, but I was a graduate student in 1987, and the story of the supernova is part of my education, so I'll tell you about it. The story starts about 168,000 years ago when a blue supergiant, a type B supergiant, collapsed in the Large Magellanic Cloud. The fact that the collapsing star managed to make it back from red giant to blue giant was surprising to theorists, but because this supernova occurred so close to the solar system in the nearby Large Magellanic Cloud, in fact, the progenitor star, being a giant star, was very luminous and was known and had been observed. And this is, I think, the only case where we have observations of a star before and then of the supernova. Remember, stellar evolution is by and large a slow process. This is one of the few cases where we really get to see a before and after image of the same star and can study it, and this forced some modifications to theory. The light from the supernova reached us in 1987, and it was the first supernova observed in 87, so it was 1987A, and the remnants of the supernova are still under careful observation. We're still seeing the development. This sequence of Hubble images starting from 1994 and ending in 2006 shows you a ring-like structure, we'll talk about it, around the supernova. The center is the remnant, and then this ring, which is progressively becoming more and more glowing and developing this blob-like structure, is an exciting thing to pay attention to. Even more famous, you can see it in the left, you see an image of the surroundings of the explosion, and then a close-up on the right-hand side, which shows you the ring I mentioned before, as well as two larger rings. I think this was referred to as the three-ring circus when it was first observed, and it took a lot of work by theorists to figure out what it is that we are seeing. The model that describes it is contained here. This was a large blue supergiant star. It had been experiencing mass loss. There was around it this envelope. That is what this blue haze there is attempting to describe in this rendition, is the emission. Remember, we talked about this, the past emissions of the bipolar emission of the star through mass loss prior to the supernova explosion. And what we're seeing, where these two extreme rings on the left and right are at a distance of 20 light years from the supernova, these are glowing where the light from the supernova is hitting the ejecta from the previous mass loss. Similarly, the glowing ring surrounding the sort of waist of the hourglass is an area where ejecta from the supernova, matter from the supernova, traveling much more slowly, is now crashing in. The remnants of the star's atmosphere is now crashing in to the previously existing gas from previous mass loss, and that's heating and compressing them, and that is the glow that we are seeing. And as I said, all of this is under study, but this was not even, but all of this, for all its excitement, was not the most exciting aspect to me of supernova 1987A. Yes, we're back to those neutrinos. So what transpired is that neutrino detectors, though they were not designed to be neutrino detectors, were active at the time. They were looking actually for signals of proton decay and found none. But the people who were looking for proton decay had large tanks of water that they were observing for small flickers of light, which we now know to be a very good way to detect neutrinos. And it transpired in the weeks after the detection of the light from supernova 1987A is that a burst of neutrinos, a total of 20 or 21 in 3 detectors worldwide, were detected at about the time the supernova exploded. And you can again remembering that most neutrinos go through most detectors completely without interacting. The fact that we saw 20 of them, you can figure out how many actually had to go through the tank in order for 20 to be detected. You multiply that by the 4 power r squared for 160,000 light years away, which is where the neutrino exploded, and you realize that this means the supernova emitted about 10 to the 58 neutrini, which, since we know their average energy, would have carried 10 to the 46 joules. This was a subluminal supernova. It was a little bit less than luminous than a typical Type 2 supernova. The reason for this, as we now understand, having seen the progenitor, is because this was a blue giant star. It had gone horizontal branch. It had shrunk. The ejecta had to escape a deeper gravitational well. They were more tightly bound. This was not a star. Typically, when we modeled supernovae, we were talking about red supergiants, very bloated. Most of the atmosphere is at large distances. In this case, all of the atmosphere would have had to have been blown away from very close, relatively, to the star's core, and this means that less energy was available to escape in the supernova. And then the fun thing about these neutrinos is when you track exactly when they were detected about 3 hours before the light was detected. Now, neutrinos, I said, are not quite massless, but they're almost massless. They travel essentially at the speed of light, but they certainly travel no faster than light. Incorrect news from a couple of years ago notwithstanding. The reason neutrinos arrived prior to the light is that the density in the shock wave of a supernova explosion, the compression, is so extreme that for the first 3 hours the light cannot escape, but neutrinos escape first, so the neutrinosphere breaks first, neutrinos escape, the ejecta have to thin for 3 more hours before light ceases to be trapped, and so measuring this time difference gave us a very good handle on checking our models of supernova, and many things were verified and other things have been corrected since. This discovery, sort of inadvertent, launched a new field called neutrino astronomy. There are many new experiments planned to try to study the sky, just as we learn new things when we turned on radio telescopes and X-ray telescopes and gamma-ray telescopes. It is hoped that observing the universe in this, for essentially the first time, in this non-light radiation, non-electromagnetic radiation, will give us a handle on phenomena that have not previously been observed. There are many neutrino experiments. One of the most fun ones to think about is this experiment called IceCube. So to conduct a modern neutrino experiment, you take a vat of very, very pure water. The water has a lot of protons and electrons in it, and if you happen to have a neutrino passing by, well, mostly nothing happens, but if it happens to interact with an electron, that electron or the products will be moving at high speed through the tank, and they will emit a characteristic kind of light called Cherenkov radiation, and then you put in light detectors called photomultipliers to detect the radiation. So all you need is a great big tank of very pure water with a lot of photomultipliers attached to it, and you need to hide this deep underground because otherwise cosmic rays and various kinds of contamination on the surface will overwhelm the neutrino signal, so you hide it deep underground where only neutrini can get. And one of the best places to do this is actually in Antarctica near the South Pole. It turns out that polar ice is not particularly transparent as we know it, but if you compress it, all of the impurities, it turns out, are squeezed out deep, hundreds of meters below the surface. Polar ice is very, very transparent, so you have ready-made a deeply submerged, huge collection of very pure water, and what the IceCube project is doing is lowering a bunch of photomultipliers, here's a depiction of the grid, into Antarctic ice and hooking them up to computers to try to detect neutrinos, and this is one of the more unusual and one of the more interesting telescopes that we have in the world, and since I was there for the actual excitement, I had to share this story with you.